we continue with the advantages of a negative feedback, and this time around we'll talk about the last advantage of negative feedback, where we have a better input and output impedance. The impedance can be increased or decreased depending on the type of amplifier. In the last lesson, we have talked about the voltage amplifier and transimpedance. So now we move on to transconductance amplifier and current amplifier. So this is a transconductance amplifier. So for a transconductance amplifier, the gain will be I/O over Vs. I over V is conductance. Okay, this is the block diagram without a negative feedback. So you have input impedance over here, output impedance over here. The Z-in should be as high as possible and the ideal value is infinity. And similarly for the output impedance, the ideal value should be infinity also. The gain without feedback is the gain I/O over Vs I mentioned just now, and if Zi is infinity, Vs is equals to Vi. So we look into the input section. Vi is actually the voltage across Zi. So using a voltage divider, your Vi is Vs multiplied with Zi divided by Zi plus Rs. Vs multiplied with Zi over the two resistance over here. And if the input impedance is infinity, it is much greater compared to Rs, so we can ignore the source resistance over here and your Vi will equals to Vs. That's why we need Zi is infinity, so we can ignore the effect of the source resistance. At the output section, the I/O is the current in the load. Okay, so we'll split into this branch, which is ATC Vi, another branch over here. So using a current divider, your I/O will be the source current over here, ATC Vi, multiply with ZO divided by ZO plus RL. The ideal value, ZO should be infinity, so it will be much greater compared to RL, so we can ignore RL. So the output current I/O will equals to ATC Vi, meaning that your I/O over here will go here. Okay, meaning that we don't need ZO because the current will be very small. With this, we can minimize the effect of the load resistance. So that's why the transconductance, the output impedance must be infinity. So now for the transconductance amplifier, the current series feedback is the feedback connection or feedback topology used in order to get the output, which is the current over here being fed to the feedback network. So if you see for current, it is in series. And at the input section over here, your Vs, Vi and the Vf, the feedback voltage is in series. So that's why it is called current series. Current referring to the output, series referring to the input section. So now we want to find the gain when we employ a negative feedback for the transconductance amplifier. At the input section, the Vs, Vi and Vf, the relationship is minus Vs plus Vi plus Vf equal to 0 using Kirchhoff voltage law, or we can simply say that Vs equals to Vi plus Vf, and Vf is beta I/O, so substitute Vf with beta I/O, and Vi is I/O over ATC. This is from the gain without feedback. Okay, ATC is I/O over Vi. So you just simply substitute Vi with that, and you have I/O, factor it out. Okay, and we want to find the gain with feedback, which is I/O over Vs. So this is Vs, I/O, rearrange this equation. So you'll get the overall gain will be ATC divided by 1 plus beta ATC. So the gain will be reduced, which is the disadvantage of having a negative feedback. Okay, but what we get is the ZIF, which is the input impedance with negative feedback, will be improved. What is the relationship between Zi and ZIF? So first, I define the current over here, which is the current through Zi, and the voltage across Zi is Vi. So I can write II is Vi divided by Zi. Okay, and Vi is just now Vs minus Vf because it is in series. So I just substitute Vi with Vs minus Vf, and Vf is beta Vo, so substitute Vf with beta IO. simplify it further. IO is ATC VI, okay? And from there, simplify it further. You have II ZI, just multiply II with ZI, so equal VS minus beta ATC VI. And rearrange this equation, so VS equals to II ZI plus beta ATC VI. Okay, so I substitute VI with II ZI, factor out II ZI, the common term over here. And my ZIF, which is VS over II, will be ZI multiplied with a factor of 1 plus beta ATC. So meaning that the input impedance with feedback is increased. Okay. Ideally, ZI should be infinity. But with a negative feedback, we further increase that value, meaning that we can have a much larger value. And for the output impedance, if you remember the previous two circuit, in order to find the output impedance, we have to either short circuit or open circuit the input. Since it is voltage, we short circuit the input. Okay. Now, with this, when Vs is 0, your Vi is minus Vf, this equation. And applying that into the output equation, there's a current entering here. This one I call Iz. The current over here is ATC VI. So I equals to ATC VI plus Iz. And just now we have short circuit this thing. Vi is minus Vf. So Vf is beta I. I just substitute Vf with beta I. So substitute everything into this equation. So I get I equals to ATC minus Vf. This is my Vi plus Iz. Iz is the current over here. The voltage across the output impedance is V. So the current will be V divided by ZO. Over here, V divided by ZO is actually the current Iz just now. And simplify this equation. Okay, I just rewrite Vf, substitute with beta I over here, and factor out I over here. Before that, you bring over to this side, and your output impedance will be V divided by I. So with this, what you get is the output impedance is also increased by a factor of 1 plus beta E, meaning that with a negative feedback for the transconductance amplifier, the output impedance will be further improved to have a very large value. The ideal is infinity. Now we move to the last amplifier, which is the current amplifier. For a current amplifier, the gain will be IO over Is. Okay, and the input impedance over here should be 0 because you want Is equals to II. So we want to ignore the effect of Rs. All the source current will be delivered to the input section of your amplifier. As for the output impedance, we want IO equals to AIII. So ZO over here should be infinity. So most of the current will flow over here and very less current at this branch. Okay, so now at the input section, using a current divider, I can find the current entering the amplifier II using this. II equals to Is multiplied with Rs divided by the total resistance over here. And since Zi is 0, so we get the value is I equals to Is. This is what we want. Okay, so we can ignore Rs. At the output section, using current divider also, IO is flowing at the RL. The source is AIII multiplied with ZO divided by the total impedance. So AIII multiplied ZO divided by ZO plus RL. Okay, and if ZO is infinity or much larger compared to RL, we can ignore the load over here. Okay, so if you look over here, if ZO is much greater, we ignore RL. So IO will equals to AIII, and with that you get this gain without feedback. IO over Is is IO over II. This is the circuit without feedback. Now we employ a current shunt feedback to the current amplifier. So for a current shunt, the first term current, so meaning that we are taking current output to be fed to the feedback network. Shunt referring to how we mix it at the input. So we have a source current, part of it goes to the input and another going to the feedback network. Okay, so at the input section, if you look over here, one equation that we can write, okay, Is equals to II plus If over here. Is, one going in and another going to the feedback network. Summation of current at that particular node is Is equals to II plus If. And since for a current amplifier, AI is IO over II, this is without feedback. and IF is beta IO, definition of your feedback network. So we want to find the overall gain, which is IO over IS. So just simply using all the equation that we have over here, IO will be AI, IS is II plus IF. Okay, IF is beta IO, substitute over here, simplify the equation, divide everything with II, so you left with AI over 1 plus beta IO over II. IO over II is AI over here, and if you rearrange this equation, you get AF is equal to AI divided by 1 plus beta A. So the overall gain, which is the gain for the current amplifier with the current shunt feedback, the gain will be reduced. And for the input impedance, what will happen? So ZIF is the input impedance with feedback, the voltage across it is VI, and the current flowing is IS. So by definition, ZIF is VI divided by IS. Okay, and we know that IS over here, there's a current go this way and another over here. So IS is II plus IF, and IF is beta IO, substitute over here. Divide everything with II. So you have Zi over, this one is 1 plus beta. IO over II will be your AI. So the input impedance with feedback will be Zi divided by 1 plus beta A. So you have the input impedance without feedback and you divide that value with a factor of 1 plus beta A, meaning that the input impedance with feedback is decreased. The ideal value should be 0. And for the output impedance, since the input is a current source, so we open the source. Okay, we're finding ZOF over here. With IS 0, your II will equals to minus IF. So at the output section, you have a current entering this node, leaving the node is IZ plus AIII. So I can write this. Okay, substitute II with minus IF because the IS is 0. Iz is the current over here. The voltage across it is V. So V divided by ZO will be the current over here. Iz is replaced with V divided by ZO. Okay. IF is beta II. Okay. The relationship between feedback current with the output current. Simplify this equation. Okay. Bring AI, BI to this side. Factor it out. Okay. And from there, you'll get the output impedance ZOF is by definition. ZOF is over here. The voltage across it is V. The current is I. So ZOF is V over I equals to ZO multiplied with a factor of 1 plus beta AI. So without feedback, the ZO should be infinity. But with the feedback, that value is multiplied. So meaning that the output impedance is further increased in the current amplifier with a current shunt feedback. So we have looked for the transconductance amplifier and current amplifier, and in the previous we looked into voltage amplifier and transimpedance amplifier. So if you look here, the input impedance or the output impedance can be either increased, decreased, both are decreased, both are increased for current series, and for current shunt it is the other way of the voltage series. So meaning that with a negative feedback, we can have a better input impedance or output impedance. We will get the value which is closer to the ideal value. And for each basic amplifier, we have a different feedback connection or feedback topology. Okay, voltage series for a voltage amplifier just now, voltage shunt is for the transimpedance, current series for the transconductors, and current shunt for the current amplifier. So this is all the relationship that you have to remember. With that, I have discussed about the last advantage of having a negative feedback, which is you improve the input and output impedance. Thank you.